To the video for the Unit 2-2, Unit 2, Lesson 2 group work that we were not able to do in class because we had a late start for the snowstorm. Before I do the group work, before I go over that, I want to do a quick explanation of scale factor. You see a triangle down here that I have created. I am going to make a copy of that triangle. I'm going to make several copies, in fact, and I'm going to use that to build a new triangle. So I'm going to put the triangles together. And I'm actually going to build a bigger triangle. And you will notice when I get the new triangle built that it is the same shape as the original triangle. In other words, all the angles are the same. So this angle is the same as this angle. This angle is the same as this angle. And this angle is the same as this angle. The sides are different though. I've made a bigger triangle. And actually this side is, instead of having a length of 10, now I have 3 10s, or equals 30. So the new side length is 30. On the other side over here I have 3 times 4 because I now have 3 4s. So I have 12. Okay. And down at the bottom I have 9 3 times, or 27. So I can take any of the sides in the original triangle, multiply them by 3, and find the sides in the new triangle. We're going to call that 3 the scale factor. What we say is that the triangles are the same scale, or the scale is the same. If I have 3 times 10 on one side, I have 3 times 4 on the other side. So I call my scale factor 3. Scale factor equals 3. That means the second triangle is 3 times as big as the first triangle, or each side is 3 times as long. So if I have a length in my first triangle, I multiply it by 3 to get the length in my second triangle. It's important to note that the scale factor could also be 1/3. Scale factors are not necessarily whole numbers. It just depends on how I'm thinking about it. If I look at my big triangle, I can take my 30 in the big triangle, I can multiply that by 1/3. To get the 10 in my smaller triangle. So the scale factor can go either way. It just depends on your problem. And I'm going to demonstrate that with another set of triangles. I still have that same small triangle, but now I have a big triangle, and I can see it's even bigger than 3 times. So I happen to know that this triangle, the side of this triangle, is 50. So to find my scale factor, I have to see how many triangles I have to figure out how to turn my pens off. There we go. I have to see how many small triangles are in the big triangle. So I'm going to take copies of my small triangle and see how many are in the big triangle. In other words, I'm seeing how many 10s are there in 50. Or I am taking 50 and I'm dividing it up into 10s. And I can see that I have 50. Want the pen again. Or my scale factor equals 50 divided by 10, which is 5. So this triangle is 5 times as big, which means that over on this side, I'm going to have 5 times 4, or 20. If I draw my triangles, I will have 1, 2, 3, 4, 5 triangles here. I'll have 4 5 times. And likewise down below, I have 5 times 9, which is 45. So I can either be given the scale factor, or I can be given the two sides, and I can find the scale factor. And that's kind of what we're going to work on in the group work. So take a look at the group work. When you feel you've got some good answers to the group work, come back and finish the video, and I will give you my answers to the group work. All right, now that you have looked at the group work, you're ready to look at this. So I'm going to start with, well, first of all, question 1. Question 1 says, list some other ways, some other examples of where you've heard the term scale used this way. So they're talking about models. A lot of times you hear the word scale model. Sometimes you'll hear people say scale it down, which means make a smaller version of something. So scale really implies that you have two objects that are similar. They're just different sizes. The scale is how different are the sizes? What's the factor between the different sizes? Okay. So to start off with question 2, we're given an example of the author having a doll made of himself. He tells us how tall the doll is. To get his height, he wants to see how tall he is. We have to go back to the wording, the text above, and it says sorry, I need a pen again. My bobblehead is a 1 to 13 scale model. So he's telling us the scale is 1 to 13. So we start off with 5.8. (2) inches, and we know he's 13 times as big. So I'm going to multiply by 13. And if you want to think about that as 13 over 1, might help later on. So I go to my calculator. .82 times 13. 75.66 inches. Okay. That's not good enough though. I want to know how much he is in feet. So I'll divide that by 12. We did that in our last unit. We've talked about it in this unit a little bit. 6.305. So I'm going to say he is 6 feet. But I have to decide what to do with that 0.305. So I'm going to take the 6 feet times 12. And I'm actually going to start with my 75.66. And I'm going to subtract out the 6 feet. So 6 times 12. And you'll notice my calculator is doing PEMDAS. It has not subtracted the 6 yet. It's going to multiply 6 times 12. 6 times 12 is 72. So I should get 3.66. So 3.66 is the number of inches above 6 feet. So I can now say he is 6 feet, and I'll round it off to 4 inches. Okay. And then he talks, question 3, about the actual mini-me. The actual mini-me was 32 inches tall, had a bobblehead made to the same scale. So his height is 32 inches. And we're talking about the scale of the bobblehead now. So the bobblehead is going to be smaller than the mini-me from the movie Austin Powers. So we're actually going to divide by the 13, or multiply by 1 over 13. And I go back to my calculator. 32 divided by 13 gives me 2.46. So Mini-Me's bobblehead doll would be 2.46 inches. So write a verbal description. Write a verbal description of the process for going from larger to smaller or smaller to larger when given a scale. I'm not going to write that because this pen doesn't write very well, but if you're going to a larger scale, if you have a scale factor and you want to go to a larger scale, you know the small, the distance on the small scale model, you want to calculate the large one, you multiply by the scale factor expressed as a whole number. If you want to go from a large one to a small one, you divide by the scale factor because you're going to get a smaller number. You divide by the scale factor expressed as a whole number. Or in the case of the one we did before, I expressed the scale factor as 1 over 13. I expressed it as a fraction and I multiplied by the fraction. That gives you the same answer as if you divide by the whole number. So either way. Question 5, they give you, say, here's a look at the map of the east side of Dubuque, Iowa. It shows a driving path from a casino on the river to a golf course on the other side. According to the Maps app on my phone, the driving distance is 3 miles. We're most interested in the graphic at the bottom left, which indicates that 1 inch on the map corresponds to 2,000 feet in real life. Okay. So down here, and that actually gives you the scale of the map. What is the scale? So the scale in this case is 1 inch equals 2,000 feet. It's a little bit different when you're talking about maps. When a scale factor before, 1 to 13, was actually 1 inch to 13 inches. 1 inch in the bobblehead doll was 13 inches in the real person. Now we have 1 inch equals 2,000 feet. So we still have a scale factor, but we have to worry about the units. So that's going to be an interesting challenge. So question 5 says points A and B are 4.06 inches apart on the map. How far is the casino from the golf course in feet and in miles? Okay. And he's talking about the straight line distance here, not the driving distance. He got the driving distance off of the app. He wants to know what the straight line distance is. So we round miles to 2 decimal places. So we've got 4.6 inches. Let me give myself some room. 0.06 inches. And we're going to calculate the number of feet. We know the number of feet is going to be a lot bigger. So we can actually multiply by the scale factor. And this is going to look like something we've done before because it is something we've done before. We call this dimensional analysis. 2,000 feet per 1 inch. Well, this is not true dimensional analysis because we're using a scale factor, not a conversion factor. You'll notice the math works the same though. I still cancel my inches, and I now have 4.06 times 2,000. And I get 8,120 feet. And I'm going to try to convert that to miles. But I'm going to have to squeeze that in down here. So I have 8,120 feet times 1 mile per 5,280 feet. And this truly is a conversion factor because there are 5,280 feet in a mile. And I cancel the feet because I have feet divided by feet. So I end up with 8,120 divided by, and you'll notice I just leave that in my calculator. I don't have to retype it. 5,280. It gives me 1.54 miles if I round to the nearest hundredth. 537, 7 is greater than 5, so I round that to 1.54. 0.54 miles. Okay. If we look at the satellite photo of the same scale, could we see any boats? Yeah, if we looked at the a satellite photo with this scale, a 50-foot boat. We take the 50-foot boat. We would actually be going down in scale. So when we had inches on the map, we multiplied by 2,000 feet to get feet in the real world. Now we have 50 feet in the real world. So we're going to use our scale factor this way. 1 inch on the map per 2,000 feet in the real world. And so now we're going to be dividing by 2,000 feet. So 50 divided by 2,000 is 0.025 inches. If I look at that, 0.1 would be 1/10 of an inch. So this is 0.025. That's actually 1/4 of a tenth, or 1/40th of an inch. If you look at a ruler, the smallest scale on a ruler is 1/16 of an inch. 1/40th of an inch would be 1/5 of that. So it would be hard to see a boat on the river in the satellite photo. So question 7, write a verbal description of the process from going to larger to smaller or smaller to larger in question 5. That's basically the same as question 3, I believe. So we start our classwork then. On our classwork, we start working with some more conversion factors. So we used dimensional analysis when we used our scale factors. We're also using our conversion factors. And you might notice I haven't been showing it to you, but we have talked about a way to set this up with equivalent ratios where you can cross multiply. So some of you might want to be doing that. But for right now, I'm going to continue kind of using the dimensional analysis. So in this first section of the classwork, we're just talking about our conversion factors. Okay? And we're talking about 2 different unit fractions. There are 2 ways to write a unit fraction. A unit fraction is something that equals 1. If I divide both sides of this by 100 centimeters, they ran together there, I apologize. I end up with 1 meter per 100 centimeters. On the left-hand side, 100 centimeters divided by 100 centimeters is really 1. So 1 meter divided by 100 centimeters is really 1. I could go the other way. I could divide both sides by 1 meter, and I would end up with 100 centimeters per 1 meter. If I'm thinking about converting from meters to centimeters or centimeters to meters, I need to use one of these, depending on whether I want to make it bigger or want to make it smaller. Same thing for number 2, write the unit fraction. First of all, I could do 1 mile per 5,280 feet, or I could do 5,280 feet per 1 mile. Number 3, 1 yard per 3 feet, or 3 feet per 1 yard. And luckily there are only 4 because I'm squeezing myself out here. I'm going to say 1 inch per 2.5 2.54 centimeters, or I can say 2.5